What is the genetic material, DNA or protein? Before 1940s, most of the biologists believed that the protein acted as the genetic material. In 1944, Avery, MacLeod and McCarthy discovered that DNA was a much more likely carrier of genetic information than proteins. In 1952, Hershey and Chase, in their experiments, confirmed that DNA was the biomolecule that carried genetic information. In their experiments, Hershey and Chase studied bacteriophage or viruses that attack bacteria. The phages they used were simple particles composed of protein and DNA, with the outer structures made of protein and the inner core consisting of DNA. This is bacteriophage. A bacteriophage is a type of virus that infects bacteria. Viruses were known to be composed of a protein coat and DNA. They grew some viruses on a medium having radioactive phosphorus and some others on medium having radioactive sulfur. Sample A was cultured in a medium of radioactive phosphorus and sample B was cultured in a medium of radioactive sulfur. The viruses grown in radioactive phosphorus had radio-labeled DNA, whereas the viruses grown in radioactive sulfur had radio-labeled protein. Phosphorus is found in DNA and not in proteins, so only phage DNA was radioactively labeled by this treatment. Sulfur is found in many proteins and is absent from DNA, so only phage proteins were radioactively labeled by this treatment. Radioactive phages treated with phosphorus were allowed to attach to E. coli bacteria. Here, only DNA is radioactively labeled. Then the phages transfer the genetic material to the bacteria. After infection had taken place, each culture was whirled in a blender, removing any remaining phage and phage parts from the outside of the bacterial cells. The viral DNA introduced into the host cell initiates replication by hijacking the host cellular machinery and make progenies of the virus. Using a centrifuge rapidly spun the samples to separate the bacterial cells from the surrounding solution. The bacterial cells are heavier as compared to virus particles and thus they form a pellet at the centrifuge bottom, and since virus particles were lighter, stays on top to form the supernatant. The progeny of the phages that were labeled with radioactive phosphorus remained labeled. Here, the bacterial pellet was found to be radioactive, but the supernatant is not showing any radioactivity. Here you can observe that the radioactive phosphorus enters the bacteria, as only the DNA was labeled with radioactive phosphorus, not the protein, which remains outside. Radioactive phages treated with sulfur were allowed to attach to the E. coli bacteria. The phages transfer the genetic material to the bacteria. After the infection of E. coli by the bacteriophage, the cells of E. coli are gently agitated in a blender. The blending process separates the phage particles from the bacteria. The viral genome enters into the host cell initiates replication by hijacking the host cellular machinery to make new copies of the virus. The bacteria were then spun in a centrifuge in order to separate the bacterial cells from the solution in which they were immersed. Here, no radioactivity found in the bacterial pellet, but radioactivity present in the supernatant. You can observe that the radioactive sulfur is in the surrounding medium and not in the bacterial cells. The progeny of the phages labeled with radioactive sulfur were unlabeled. The progeny of the phages that were labeled with radioactive phosphorus showed that their DNA contained the phosphorus radioactive label, whereas the progeny of the phages that were labeled with radioactive sulfur no showed any sulfur radioactive label in their protein coat. So, from this experiment, Hershey and Chase concluded that DNA, not protein, was the genetic material. They determined that a protective protein coat was formed around the bacteriophage, but that the internal DNA is what conferred its ability to produce progeny inside a bacterium.